All right, guys, how's it going? So today we're going to start a new section. It's going to be on antiderivatives. And so what is an antiderivative? Before we even jump into the definition of it, even though I have it written out here, I kind of want to talk about the idea of what an antiderivative is. Okay, so far in our class, we've been focusing solely on derivatives. We know that derivative is the rate of change, it's the slope of a graph, it's the tangent line to a graph. So what exactly is an antiderivative? And if we know how to find derivatives, why would we want to find antiderivatives? Well, that's a really good question. In applications, right? So remember, it was a couple weeks back, actually, more towards the beginning of the semester, when we were looking at derivatives, we were able to find from the position function, we were able to find velocity and acceleration. But what if we know acceleration and we want to know the position function? And so what antiderivatives allow us to do is to work backwards from the derivative to obtain further information. And then the next section over, we're actually going to talk about how antiderivatives relates to the area under the curve. But for this section, we just want to focus on the idea of antiderivatives itself. So antiderivatives is exactly what it sounds like. It's the opposite of a derivative. So remember that for a derivative, to find the derivative, if we have a function, we use the power rule. And now somehow we're going to use, in order to find the antiderivative, we're going to have to do some kind of a backwards power rule. Sounds a little bit odd, but I'll show you exactly what that means. So here's a formal definition of an antiderivative. A function f, so this is a capital F, a function f is called an antiderivative of f on an interval if the derivative of f capital F prime of x is equal to this function for all x and I. All that means is that if we have a function, the antiderivative will give us this antiderivative. If we take the derivative of this, will give us exactly that same function. So let me illustrate this with an example so that you guys can kind of see what I'm talking about. So let's consider if we had a function, if we have this, for example, if we took the derivative of, let's say, a polynomial, doesn't matter what polynomial, let's say 3x squared plus x minus 5. If I asked you, hey, compute the derivative of 3x squared plus x minus 5, you're like, easy, Miss Gonzalez, I got you. We would just use the power rule. We're dealing with a polynomial, nothing too fancy here. Do the power rule, bring the 2 up to the front. This is just x, so it's going to be 1. And so my derivative of this is just 6x plus 1. Easy peasy. Okay, perfect. So the antiderivative of this one here is specifically what's inside here, because this here is the derivative of this function, but this here is the antiderivative of this function. But there could be many different types of antiderivatives that give you this exact same thing here. And one of the biggest reasons about that is that when we took the derivative of this constant didn't really matter to get us this here. We could have put in any constant here and still gotten this antiderivative as long as this part stayed the same. So that's the idea about a antiderivative. You could go forwards, you could go backwards. Just by taking the derivative of the antiderivative will take you back to the original function. So the whole idea on antiderivatives is that we want to go backwards. That's all we want to do. So now we want to go back. basically backwards. So let's just focus on a little piece of this function. So I'm going to go and I'm going to focus on some random derivative. So if I have the derivative of x cubed, right, I know that to take the derivative of this, I'm going to multiply by 3 to the front. So the first thing is I always do is I multiply by 3 to the front. So I take that exponent, move it over to the front. And then my second job is to decrease the exponent by 1. So we decrease the exponent by 1. Easy. You've been doing this whole semester, basically. And so when we take the derivative of this, we just get 3x squared. Perfect. But if we wanted to go backwards, how would we even do that? If we wanted to go backwards from here, how would we do that? So what we want to do is, this is what going back means. We have to figure out a way to go back to the original function, to this function here. And we're going to call that, when we find the antiderivative, we're going to call it capital F of x. So going back means that if we, in order to get the derivative of x cubed, we multiplied by 3 and decrease the exponent by 1, now instead of decreasing the exponent by 1, we're actually going to increase the exponent by 1 or add the exponent by 1. So going backwards means that we're going to 1 increase the exponent by 1. And 2, we are going to divide by the new exponent. So this is something that's actually new. And I'll show you exactly how we would do this. So we're going to divide by the new exponent. New exponent. Perfect. Okay, so we have that RF right now from the derivative that we got is 3x squared. Now I want to apply what we stated here to get the antiderivative. So if I say I want to get the antiderivative of this, right? Then according to what I just learned here, I have to increase the exponent by 1. So I'm going to leave this 3 in the front. I'm going to do x. I'm going to do 2. And I'm going to increase my exponent by 1. And then I'm going to divide by the new exponent. So I'm going to divide by 2 plus 1, which is 3. Now, I'm going to leave it at this for right now, just so that you guys can see what's happening. This is going to equal, eventually, the 3's will cancel out with the 3, and then we'll be left with x cubed, which was the original function. And we could always check that again by saying, okay, well, if I take the derivative of this, am I going to get this? And yeah, if you take the derivative of that, you will definitely get 3x squared. So that means you have the right antiderivative. But here's the thing, we're not done. Because if we consider that if I added something like plus 3, the derivative of this is still this function. So because of that, instead of writing 3, we are going to write plus c. So my antiderivative is capital F of x, which is equal to x cubed plus c. And that's because c could be anything, and no matter, c could be any constant. Let me specify that, not anything, it has to be a constant. But c can be any constant, because no matter what, if I take the antiderivative of, if I take the derivative of capital F of x, I will still get 3x squared because that constant, when we take the derivative of it, is just 0. So nothing really happened there. So I want you to try one on your own. I know it's a little bit weird to think about doing the derivative backwards, and we'll learn many we'll learn many antiderivative techniques moving forward. And in Calc 2, all you'll be doing is doing the antiderivative over and over and over again. More than half that class is antiderivatives, just like Calc 1 was all about derivatives. Now, since we're approaching the end, I really want to prepare you for your Calc 2 class, so we're going to be focusing on antiderivatives. And moving forward from here on till honestly Calc 3, Calc 4, you'll be doing antiderivatives forever. And derivatives still too, so don't ever lose that. So let's have you try one. I'll do it with you also, but try on your own to take the antiderivative. We'll do a really simple one just so that you can get the hang of it, but try this one. So go ahead and pause this video and take the antiderivative. So find your capital F of X for this one. So try it on your own, and then let's see if we get the same answer. Okay, so hopefully you had time to try it on your own and just didn't keep going with the video. I really want you to try. So we need to increase my exponent by 1, and then I'm going to divide by my new exponent. So if I increase my exponent by 1, that's increasing it to 3. So then that's going to be x, and my new exponent is 3. And then I have to divide by that new exponent. So I'm going to divide by 3. And now let's do a little check. I want you to get into the habit, especially right now, that you're just learning antiderivatives. Eventually, you won't have to check them anymore, but this is like a really good check to say, hey, did I do my antiderivative correctly? Because this is so easy to check, because in order to check this, all you have to do is say, okay, let me take the derivative of f of x. If I take the derivative of capital F of x, and I find f prime of x, I'm going to, let me rewrite this. So this is 1 over 3x cubed. If I take the derivative of this, now it's going to be, I move the 3 up to the front. It's going to be 3 over 3, which is 1, and decrease it by 1. The derivative is definitely x squared. So that means that we actually have the correct antiderivative. Perfect. So we have the correct antiderivative, but like I said, there's many different derivatives, because we also have to consider, like, what about if we had f of x is equal to capital F of x? So if this was my antiderivative, was 1 over 3x cubed plus 125. Or what if it was 1 over 3x cubed plus 3? Or 1 over 3x cubed minus 7? No matter what, if I take the derivative of any of these, I'm still going to get x squared. So we have to specifically say that the antiderivative is actually capital F of x, which is equal to 1 over 3x cubed. This part doesn't change, but because I can put any constant in this position, and I take the derivative of it and it goes to 0, I'll put c as my constant. Super important here that you don't forget to do this plus c. This plus c is life, because a derivative can vary by any constant, and you'll still have the same function. Because remember, the derivative of any constant is just 0. So you need to put this plus c here, saying, hey, we have some constant. We don't know exactly what it is, but maybe in the future, I can figure out how to find that constant. So please keep that c there. If you've taken calculus before, you know how important this c is. And if you have any brothers or sisters and you ask them, hey, do you remember plus C in calculus? And they'll probably have nightmares about it because they accidentally forgot to put a plus C on an exam. And then it was like minus the whole problem. Yeah, don't forget the plus C. It's conceptually really important that you keep this plus C here. I'm not going to stress that enough. So please, that plus C is your life for at least right now for these antiderivatives, because we don't know how the antiderivative, what the constant is that belongs right here. But we know that there might be a constant. It might be just zero. I don't know. But we need to report that there is some constant we don't know about, but it could be right there. Okay, so this brings us to a theorem, which is really just what I just said out loud over and over again. So this theorem, it's in your book too, is if capital F is an antiderivative of F, oh, what happened? Of F on an interval I, then the most general antiderivative of F on I is F of X plus C, where C is an arbitrary constant. So this is just putting what we did in the example into words, into a theorem. And so this is just saying that this is always going to be the most general form of your antiderivative. And now, before we do a couple more examples on this, because this is kind of like derivatives all over again, the best way that you're going to get good at this is by doing a bunch of problems over and over again. Just like when you were learning all the rules for derivatives, and now we're kind of going to shift that to antiderivatives. So we're going to be doing that over and over again. So what I want to do is I want to introduce some notation for you, which they don't start talking about till chapter 5. It's at the beginning of chapter 5, but I think it's a good place to introduce it right now, which is what's going to be called the integral sign. So we're going to introduce some notation here, just really quickly. Now for this section, we're not actually going to use this notation, and I don't think that they use this notation too much in this section. I know they use it more in the later section, but this is how we are going to notate an antiderivative. So if you ever see this notation, it's kind of a funky looking notation, but it's not that bad. Just remember that when we introduced the derivative, we also had notation for it. So recall that when we introduced the derivative, we had two types of notation. We have the prime notation, which is Newton's notation, and then we also had Leibniz notation, which was d over dx, to say that we're going to take a derivative. And so just like how we had a notation for derivatives, we also have notation for antiderivatives. And like I'm going to say this, you won't see it too much in this section, but I just want to give you a little bit, I just want to give you some insight into what it's going to look like so that when you see it in, I think 5.1 or 5.2, you don't get all freaked out. So don't worry about this too much right now, but just keep this in your mind. This is the notation for when we're taking an antiderivative. So the notation is notated by like a weird looking S. This is called an integral. And so when we say antiderivative, we can also say we are going to integrate some type of function. And so, for example, the way we would do this is we would say that the integral of, let's say, 5x to the 7th power, and then we'll end with a dx. So this is what we're integrating with respect to. And again, I'll go over this again one more time in a later section, but I just want to introduce it. Okay, so if we want to take an integral, what we're going to want to do here is, since this is a constant, I could actually pull it out of the integral. And again, I'll establish these rules more later on, so don't get all freaked out right now. And so we can pull out that 5 because it's a constant, and then we get x to the 7th dx. Okay, so when we have this, what this is telling us here is that we need to integrate x to the 7th, which means that we need to find the antiderivative of x to the 7th with respect to x. That's just telling us that, hey, we're finding the antiderivative of x, of that variable x. So we're not doing some random variable like t. So this has to match or inside variable. And so then to integrate this, remember that to get the opposite of a derivative, what we're going to do is we're going to add 1 here and then divide by it at the bottom. So once you've done that, we still have this 5 outside. Now what you can do is you're going to do the x to the 8th over 8. And once you take the antiderivative of something, or the integral of a function, you no longer need to write this notation anymore. I just did brackets because I have this 5 on the outside, so I have to remember that I have to distribute it back in later on. But I'm not done here. Remember that your antiderivative can vary by that constant that we talked about up here. So just keep that in mind, so we're not completely done with it. This is going to be plus some constant c. Don't ever forget the c. I don't know how much to stress this, but don't forget the c when we're doing antiderivatives. Look how much I'm circling this. Don't forget the c. It's almost gone. Don't forget it. All right. And now what we want to do is now we're going to distribute this 5 in. Okay. And it's going to sound a little bit weird, but when I distribute the 5 in, I'm going to get 5 over 8. Nothing too crazy here. X to the 8 plus c. Now here I don't need to write 5 times c or anything, because here's the thing. I don't know what c is, so it doesn't matter. It doesn't matter what c is, because if I distribute it in a 5, I don't know what it is, so I don't want to write 5 times c. I'll just leave it as c, because no matter what, this is still representing a constant. And since this is a constant, and that represents it's a different constant, but it's still a constant. So just leave it as c. There's no need for you to write 5c. It doesn't really matter. Okay, and so let's do a couple of examples.